So today we are going to study bivariate normal and some transformation for that. Bivariate normal is a very common and useful bivariate model for a continuous pair of distributions. The distribution can be modeled in many different ways, but there are certain nice features are available for bivariate normal, and not only bivariate normal, it can be also generalized to multivariate normal with a very nice properties. That's why the application of this general version of normal distribution or the random vector following normal distribution is very much popular in statistics and as well as machine learning and many other areas. So let us define first the bivariate normal density function, because again, as the closed form of the distribution function is not available like the normal distribution, we characterize it first by the density function, and you can also use the moment generating function, characteristic function, all those things. But let us start with the PDF. Oh, sorry. Yes. So let us define its PDF. It is two random variables, x and y, said to be, or the pair of random variable you can say, is said to follow bivariate normal distribution okay. With expectation of x, marginal expectation of x is mu x, marginal expectation of y is mu y, variance of x is sigma square x, variance of y y is sigma square y, and correlation of x and y is rho. Okay. With this specification, if it has the following density, it has the following PDF, and the notation is this: x, y follows normal. Sometimes people also write n2 just to denote how many dimensions are there. But okay, in general, it is mu x, mu y, sigma x squared, sigma y squared, rho. So this is the way of writing. Let us define the PDF. This is f x y e to the power minus half. So this entire thing within bracket. So e to the power minus half into 1 upon 1 minus rho square, and then there will be a big component x minus mu x by sigma x whole square plus y minus mu y square minus 2 rho x minus mu x by sigma x, y minus mu y by sigma y. This entire thing is in the exponent, and then the whole expression divided by root 2 pi square, that means it is 2 pi sigma x sigma y into square root of 1 minus rho square. Typically, in this situation, mu x belongs to R, mu y belongs to R, sigma x is greater than 0, sigma y is greater than 0, rho belongs to. Theoretically, it can be done for -1 to +1 closed interval. Let us consider -1 to +1 open interval for the time being, such that no trouble is there. Okay, so these are the specifications that we need. Okay, already we have shared the PDF, and we will discuss about that. And rho, notice one thing here, that when rho equals to 0, f of xy is nothing but e to the power minus half x minus mu x by sigma x square plus y minus mu y by sigma y square whole divided by root 2 pi square sigma x sigma y. So it is the product of the two densities. Marginal density, x is following normal mu x sigma x square, y is following normal mu y sigma y square. This is true in general, but when this is true in general, whatever may be the value of rho, but when rho equals to 0, this is true. So rho equals to 0 will imply independence for bivariate normal. It is not always true. Already we have told that we will see this example, and today we can observe it, that when rho equals to 0, bivariate normal splits into two parts of the marginal product of the marginal densities, and as a consequence you have the independence. So can you give an example for such a distribution? Any example? Height weight distribution is a very common example. Height weight distribution. Anything else? It can be also like say this is one common thing that if you measure this length of your hand, so and that is the same as the palm length from here to here. So your palm length and your height and palm length and height. So all these are examples for and if you measure that, then these two has a very high correlation. Eventually, you may find that your height is almost approximately 8 times of your palm length. Fluctuation definitely will be there, but this is a very nice observation. Okay. And in a similar way, different sizes of the bone of the bodies, all those if you consider together, then you can also think of a multivariate normal distribution. Similarly, if you consider the price of oil and at the same time price of another some commodity like sugar, or maybe which is need more transportation, the dry fruits in the market, all those things are dependent variable and you can model them with bivariate norm. Okay, now let us talk about its theoretical property. The interesting fact that we specially look for is the conditional distribution of the bivariate normal. That means the conditional distribution of y given x. So here we are interested for, so when x, y follows bivariate normal mu x, mu y, sigma x squared, sigma y squared, rho, then the conditional distribution, of y given capital X equals to small x, or in other words, the regression of y on x is given by that y given x follows normal distribution with mu x plus rho times sigma y by sigma x, x minus mu x into 1 minus rho square times sigma y square. Okay, we will prove it. Notice one thing here, that this regression is linear. That means expectation of y given x equals to small x is mu x plus rho times sigma y by sigma x into x minus mu x. So if you split it, this is mu y. So this, if you split it, you can get this part as mu y minus rho times sigma y by sigma x plus again rho times sigma y by sigma x into x. So this is of the form a plus bx. So this is the intercept. This is intercept, and this is the slope of the line. So it is a linear. And second property that you can immediately get from here is this, that the conditional variance, so variance of y given x equals to small x equals to 1 minus rho square times sigma y square, which is definitely less than the unconditional sigma y square, which is the unconditional variance of y square. So this is a very important observation, that when we, and this is almost in general true, that when we do regression, the variance reduces because we are looking for the variance of a subsection of the data. So it is less than the entire variance that we usually observe. So now it is our job to find out the conditional distribution of y given x, and you can immediately do the same way the regression for x given y. It need not be on only y given x. You can also have the regression based on x given y, and you need to adjust the coefficient and the variables accordingly. Okay, so before we do the analysis, this is the tricky part, not so difficult, but what we have to do is we need to split this entire expression into a perfect square. Okay, so may I beg your pardon, I need to use washroom. Please give me for 5 minutes, just for 5 minutes. Yeah, sorry. Okay, so to identify the conditional distribution, first we need to split the exponent part into a perfect square and the rest part, and from there it will be trivial for us to obtain the conditional distribution. So let us do that. So the exponent part is this, especially this part. Let us first take care that x minus mu x by sigma x square plus y minus mu y by sigma y square minus 2 rho x minus mu x by sigma x into y minus mu y by sigma y. Now let us consider this quantity first. Y minus mu y by sigma y whole square minus 2 rho okay, y minus mu y by sigma y into x minus mu x by sigma x. Now if I write rho square times x minus mu x by sigma x square, then this quantity will be a perfect square. Then I have introduced this part, so I need to adjust the same in this way. Already x minus mu x by sigma x whole square is present there. So 1 minus rho square into x minus mu x by sigma x whole square. Okay. So this is the expression that you already and immediately you can have. So now if you want to write the joint density again, f x y, then you can write in this way. So let us call this quantity that q. So this joint density is nothing but e to the power minus half 1 minus rho square q whole divided by 2 pi sigma x sigma y 1 minus rho square. Is it okay for everyone? Hello? Is it fine?
Yes, sir, it's fine.
So now this 1 minus rho square and this part from here 1 minus rho square, they will be cancelling each other. It is immediate. So we will be able to write the thing in this way, that okay. So this is e to the power minus half y minus mu y by sigma y minus rho x minus mu x by sigma x. This quantity square should adjust it with 1 minus rho square, and this part, another part, e to the power minus half x minus mu x by sigma x whole square. Now the denominator part we can also split into two parts. root 2 pi sigma sigma y into square root of 1 minus rho square, and here root 2 pi sigma x. Okay. Now from here, let us try to see what the adjustment we can do. If we take sigma y out from this expression, then we will be able to write it 1 minus half 1 upon sigma y square 1 minus rho square. This is one part multiplied with let us see, this will be y minus mu y minus rho sigma y by sigma x into x minus mu x. This entire quantity square whole divided by root 2 pi sigma y square root of 1 minus rho square into the rest part is as it is, e to the power minus half x minus mu x by sigma x whole square whole divided by root 2 pi sigma x. Now you can observe here that this is the marginal density of x, because if you integrate out with respect to y, this entire expression will give you 1. Is it okay? Check whether this part is okay or not. If you integrate this entire expression with respect to y, although there are x present here, if you just integrate out, because here y is not present, so whenever you will integrate fxy with respect to y, that will impact only in this part, and it is a full form normal density for y with mean part as written here and the variance part as written here. So if you integrate out fxy with respect to y, you will get e to the power minus half x minus mu x by sigma x square by root 2 pi sigma x. If you integrate this entire expression with respect to y, you will get this. So as a consequence, what you will finally observe that f of y given x, that is fx y by fx x, this quantity is e to the power minus half 1 minus rho square sigma y square into this y minus mu y, space branch, mu y minus rho sigma y by sigma x, x minus mu x square whole divided by root 2 pi sigma y 1 minus rho square square root of that. So this is nothing but fxx is the marginal density, and this is the conditional density. So as a consequence, what we have already claimed that the conditional mean is this and the conditional variance is this. So y given x is following this, and in a symmetry, can you please tell me what will be the conditional distribution of x given y? Please tell me from the symmetry.
So it'll just be normal mu x plus rho sigma x by sigma y.
Sigma x by sigma y, correct?
Into y minus mu y.
Y minus mu y. This is the mean part complete. 1 minus
yes,
rho square as it is, and again sigma x square. So this is from symmetry. So this is the entire structure of bivariate normal, its conditional distribution, and interestingly, this is linear. This helps a lot in say for example, another very nice example that all of us has done in our school days. Say for example, if you have asked to fit or find out the refraction coefficient from say air and glass or air and glass and water, whatever may it be. So usually people, what they do, they just plot the data points and somehow they draw a line. But that is not the correct way to do, because first we have to fit a model for the data, and then what we are supposed to do, that we need to find out what is the intercept, we need to find out what is the slope, and then we first need to check whether the intercept is passing through the origin or not, and then we need to identify or do a proper testing whether the refraction coefficient is as given in the book, or maybe whatever is the number, exactly the same or not, because the water density is different at different temperature, air density is also different at different temperature. But at least the linearity of the line is ensured. So in future, maybe in regression course, we will see that how we can do some testing related to this intercept. Suppose it is, if it is a refraction problem, then you are supposed to check whether A is significantly 0 or not. From your data, it did not be exactly 0, but whether it is very close to 0 under certain variation, that we can check, and we can also cross check for the value of the slope. Okay, so that is also another interesting thing where we can use this bivariate normal model. We can assume that each of the observation, x component and y component, angle of incidence and angle of refraction, both of them are suffering from some error, and sign of that has some normality error, and we can immediately fit a bivariate normal model for those data, and we can obtain the values of A and B, and then we can cross check. So this is another nice application of bivariate normal. So let us see some diagrams that already we have shared, so that we can have a better interpretation of the model. Okay, we are starting the joint density. Here. So here is a typical bivariate. Can you see this PDF?
Yes, sir.
So this is a typical PDF of bivariate normal, a dome-shaped surface, and each of these grid lines, they are nothing but the conditional, representing the conditional density of y given x. For a fixed value of x, this is the conditional density of y, and for a fixed value of y, this curve will be a conditional density of x. And if you just want to see its data version, such that the data you can observe in this form, that if this part is the scatter plot of the data depending on x and y, you observe the values of x and y and you plot them on a plain paper. But when you see the marginals, that means it's x coordinate and y coordinate, then its x coordinate will follow a normal distribution individually, y coordinate will also follow a normal distribution individually. But notice one thing, let me just here tell you that it is a very much alarming note, that even though x and y individually follows normal distribution, xy jointly may not follow bivariate normal. Example can be constructed, but I'm just leaving it uh, for your course. Uh, x and y marginally may be following normal distribution. That doesn't guarantee that they will jointly follow bivariate normal. But the reverse is true. If they jointly follow bivariate normal, marginally they are always normal. Okay. So remember this thing. Very important feature, that one is the starting from here. Rho equals to 0 implies independence. This is a special case. Then regression line is linear, regression variance is less than the unconditional variance, and even though x and y are individually following normal distribution marginally, their joint density need not follow a bivariate normal. Okay. Okay, so now let us go for it. Here are different diagrams related to, here are different diagrams related to the different values of sigma x, sigma y, and rho. When rho equals to 0, it represents independence, and when sigma x, sigma y are same, then the contour plot. Do you know what is contour plot? Hello? Do you know what is contour plot? Anyone?
Yes,
Okay, so let
repeat
me
that.
just बोलो बोलो बोलो. Yes, go ahead.
Sir, it is a diagram where we show regions of same height with circular.
Yes, yes, exactly. We are looking for the same height. So technically speaking, this is the thing that we are looking for all those xy values. Um, so all those pair of xy values such that fxy is some constant. Okay. So let us say ck. If I change the value of k, this will change. So this is the contour plot, contour for fxy equals to k. So this is just a collection of all those points for which the surface fxy has a fixed height. Or you can imagine in this way that you have that surface and you cut the surface with a horizontal plane. You cut the surface with a horizontal plane. So wherever it is cutting, that projection of all those points on xy plane will give you the contour. So that is the meaning. So here, if your sigma x and sigma y are same, it will look like a circle. Okay. Now, in most, I think, rest of the all of the cases, it will look like an ellipse. Now, if rho is positive, it will be right-sided tilt. Okay. Although sigma x, sigma y are same, it will appear right side tilt and ellipse. If rho is negative, it will be tilt to the left side. And if rho is 0 and sigma x, sigma y are different, then you can have the shape of ellipse in a different form, which is either it will be depending on the principal axis A and B, whatever, some will be more, some will be less. Again, it has a different sigma and non-zero rho, and again different sigma with non-zero negative rho. Okay. Here you can see the conditional densities of the y given x. So for different values of x, so let me make it large. So different values of x. So if x equals to a, then the conditional PDF of y given x is this blue color. If the value of x is b, then the conditional distribution of y given x is this green color, and if the x value of c, then the conditional density of y given x is this red color PDF. And you can observe that depending on the value of x, mean values are also changing and variance is also depends on the fact that where it exactly is. Sigma 1 minus rho square sigma y, it depends on the situation because of the rho value. It will vary. Okay. Now here also another diagram. Okay, so last few diagrams I have copied from the internet, and you can also get more diagram from the internet itself. So here itself, you can see that this is the conditional density of x1 given x2 in this way, and here also this is mu1 for x1 and this is the marginal density for x2. I think that's it. Here now we are going for a few transformation, and if you try to remember whatever we have studied so far, we have, in most of the cases, we have started with uniform distribution. Then through different transformations, we have reached certain distribution. Okay. But the normal distribution, we have directly stated its PDF. And we could not obtain one normal distribution from uniform distribution. So many other distribution we have got. So from normal, so from uniform to exponential, exponential to gamma, gamma to beta, then we have associated gamma with chi-square, so on and so forth. All those things we have got from the transformation. But one normal distribution we could not obtain from one uniform distribution. The reason is that we cannot do, but what we can do is we can obtain a pair of independently distributed normal random variable from a pair of uniform distribution independently. So that thing we are going to study now. So before that, let me just show you the diagram. This method of generation of normal distribution, paired bivariate normal with mean zero variance one, both of them independently. That method is known as the Box-Muller method. It takes the data from uniform distribution. As you can see that U1, U2, they are following uniform distribution from 0, 1 to 0, 1. And this is this blue square representing the same thing. And after the transformation that we will discuss now, you can have the scatter plot of the normally distributed random variable. They are independently distributed and they are standard normal marginal. And already you have seen if they have the same variance and rho is 0, then you have a circular contour. And you can see that these pink dots are almost distributed over a circle. And if you take the properly contour, you will eventually get those circular pattern. Now, if you see the marginals, then also you can see that they are following standard normal distribution. So this is a very interesting thing that we are going to study now. So before we go for this study of the transformations, do you have any query related to bivariate normal? Any query? Okay. If not, then let us continue. So, okay, so we can just change it also. Okay, now we are going to study the transformation of random vectors. Rather, already we have done the study of transformation for univariate random variable. So today we are going to introduce transformation of random vectors. Okay. So let me tell you the result first, and then we will go for the derivation. So let x, y, first let us do for the bivariate, multivariate can be generalized. Be continuous valued random vector with PDF fxy, then the PDF of, say, in this way, uv, another pair of random variable, which are u is a function of xy, v is also a function of xy. Okay, both of them are function of xy. So this is nothing but a transformation from R2 to R2. Can be given by, say, GUV, which is nothing but, if you consider, if x in terms of u and v, y in terms of u and v, that is the reverse transformation, multiplied by first the derivative of the Jacobian, the old, by new. So this is a matrix. This derivative will give you a matrix, and this symbol is for determinant, and this, maybe say, another symbol is for absolute sign. Okay. So where del xy by del uv is the Jacobian matrix, this one stands for determinant, and this outer one stands for absolute value. Because if the determinant becomes negative, that is not of any use, because we are eventually calculating the density, and density function cannot be negative. Same thing you have already seen when we have studied the univariate case. So this is nothing but a problem of transformation of variable in integration. So method of substitution, or whatever maybe you call it. So this is eventually the problem of the transformation of variable in integration. Now, or also we should write this one as the xuv is the value of x in terms of u and v, and yuv is the value of y in terms of u and v. So all this. So can you please tell me what exactly the Jacobian gives to you? This one, this derivative. So del x y by del uv, that is nothing but del x del u, or you can go by anyway, del x del u, or del x, sorry, del y del u, then del x del v del y del v, this matrix. What it exactly gives to you, or its determinant eventually it gives to you.
So is it the gradient?
Say again, please, louder.
So is it the gradient?
It eventually gradients type of thing, but if you, okay, so I'll try to understand with this simple example. Let us consider a transformation from R2 to R2. Okay, in this way. Suppose you have a unit radius circle. X square plus y square equals to 1. Okay. What will be the area?
So pi.
Pi. So area is pi 1 square is pi. Now I am doing the transformation in this way that uv equals to a0 0b xy. What will be the equation of u and v?
So
What will be the
the
relation?
ax and by.
Um, okay, so yeah, so ax plus by equals to 1. Okay, from this one. But if you want to write that equation in terms of u and v, what will you get? So from here, what you get? U equals to ax, v equals to by.
Yes, so
And
it'll be u by a square plus v by
u
b
by
square.
a square plus v by b square equals to 1. So the transform thing will be, depending on the values of a and b, doesn't matter, ellipse, right?
Yes, sir.
And what will be the area?
So pi ab.
Is pi a. Now, if pi a into b. Okay. Now, if I consider this matrix as a name as T, then is it not pi into determinant of T?
Yes, sir.
Right. And so here in this transformation, if you take the derivative of, say, del u by del x, or maybe del u v by del xy, you will get this matrix.
Yes, sir.
So eventually the Jacobian is giving you the instantaneous rate of change of volume. The Jacobian is eventually giving you the instantaneous rate of change of volume that we need to incorporate in the expression of density, because when we will calculate, we have to probability, we will eventually calculate the area under the curve. So how much change is happening in the base xy plane, that thing we need to capture. Height will be captured by this part. Base area will be captured by this part, and then if you take the sum or integration, whatever may it be, then it will be the probability. So height of the variable will be captured by this part, and the base area will be captured by this part. So eventually this is the relation. Here a and b, they are fixed constant, that's why you are getting such a nice form. Every time u and v need not be always such a linear transformation. it will have many other form of x and y, but the same thing can be tackled with this in general derivative. Okay. So that is the motivation of having this term Jacobian term in the expression like this. Okay, so let us have a quick example. We will gradually develop the complicated problems, and eventually we'll show that proof of the Box-Muller method. So example 1, let x, y follows IID normal 0, 1. Define u equals to x plus y and v equals to x minus y. Okay, and you need to show that this follows normal, show that normal 0, 2. This will also follow normal 0, 2, and they are independent. Okay. So many things are together. It is very simple. Let us go step by step. So first, try to express x in terms of u and v. So x equals to u plus v by 2, y equals to u minus v by 2. Then let us consider the Jacobian del x del u del x del v del y del u del y del v. Can you please tell me what will be the values? Already you have the equation.
One by two.
Say half this one, again half, this one is again half, this one is
Minus.
minus. Okay. So determinant of j is minus half, right?
Yes.
And absolute value of determinant of j, that means is half. Okay, fine. Now the joint PDF of, let us write down the joint PDF of xy is, say, fxy. Because they are independent, it will be the product of the marginal. So e to the power minus half x square plus y square divided by 2 pi. Is it okay? Because they are the product of the marginals. Now let us write down the joint PDF of u and v. Of u and v. So let us call GU. Here I need to plug in x in terms of uv, y in terms of uv first. So that is f of, say, okay. Okay, so let me write u plus v by 2, u minus v by 2 into this. That's it. So this quantity you will get e to the power minus half u plus v by 2 whole square plus u minus v by 2 whole square. This quantity divided by 2 pi. Jacobian is half. Absolute value of the Jacobian is half. So eventually, if you split them, what you will get from here, that e to the power minus half u square 2 times, and in denominator it is 4, so it will be u square by 2. Again, same thing will happen for v. Cross product term will cancel. V square by 2. Here you have 2 times 2 pi. So what you can write, this e to the power minus half u by root 2 whole square divided by root 2 pi into root 2. Similarly, e to the power minus half v by root 2 whole square divided by root 2 pi into root 2. So that satisfies all the claims. Following normal 0 2, V is following normal 0 2, and their joint density is the product of their marginal density, so they are independent. Any problem? So UV are IID normal 0 2. That's it. Any problem here? Is it okay for everyone? Okay, so if it is fine to everyone, let us go for the next. So this is now from Cartesian coordinate to polar coordinate. So let xy follows IID normal 0 1, and find the distribution of r and theta, where x equals to r cos theta and y equals to r sin theta. Okay. Definitely r is greater than 0, theta belongs to 0 to 2 pi, or maybe you can take it from minus pi to plus pi, that is also okay. Whatever way you want, you please take it, no problem. Now tell me, how will you do this one?
So we begin by writing r and theta in terms of x and y. So r would be square root of x square plus y square.
R is no, but the fact
I
is that
mean,
what you eventually need is you need the old variable in terms of the new variable, right?
yes, sir.
And that is
Okay.
already given.
Oh, yes, sir.
That is already given. So better you take care of the Jacobian.
Okay, sir.
Jacobian, but I think you remember this one, right? What it should be? Can you please tell me?
So it will be
So
cos
1 by
theta.
r. Oh, wait, so let
So
me
it's
just check.
dx by dr, rho x by rho r. No?
Dx by dr, dx by d theta. Yes, in this that way.
So the first row, first column will be cos theta.
Mm.
And then it will be minus r sin theta.
Mm.
Uh, next one will be sin theta and r cos theta.
Okay. Take the determinant.
The minus r sin theta.
R only, right?
Yes, sir, r only. Yes.
Okay, it is R only, and R is positive, so nothing more to do. So the Jacobian is R, or the determinant of the Jacobian matrix is R, and it is greater than 0, so our life is easy. Now write down the joint density of xy. Joint density of xy is fxy, and that is e to the power minus half x squared plus y squared root 2 pi. Now x we can write r cos theta, y we can write r sin theta. Okay, but for that let us go for the joint density of r and theta of r theta. Let us call g small r theta. Let us write it down in this way, that e to the power minus half r cos theta whole square r sin theta whole square divided by 2 pi multiplied by small r. I am just using as a small notation of capital R as small r. Okay, r greater than 0, theta minus pi to plus pi. Okay, now here you see that cos square theta plus sin square theta will be 1. So e to the power minus half r square into r. This is one part. Another part is 2 pi. Okay. And here, from here, we can say that GR, the marginal density, is R times e to the power minus half R square when R is greater than 0, 0 otherwise, and G capital theta of small theta is 1 by 2 pi, where theta belongs to minus pi to plus pi, 0 otherwise. So theta is following uniform distribution. This distribution has a special name. This is uniform. And this distribution has a special name. It is called the Rayleigh distribution. Why? It is pretty simple that when you have this xy values, so different point, and then if you just consider the r values for each of the xy, then it seems like that a point source of light and is emitting from there. So all these blue lines are the different values of r for different pairs of xy, and so these are the values of r. So that's why this is known as the Rayleigh distribution. Okay. Now, can you tell me what is the distribution of r square? Let us now start our work in terms of the Box-Muller method. Whatever we have taught so far, based on that, can you please tell me what is the distribution of r square by definition? This is the thing that you have got. Okay. But from definition, from the scratch definition, can you please tell me what is the distribution of r square? We are trying to build the connection. Okay, so now let me tell you in this way again. X is following normal 0, 1. Y is following normal 0, 1. And they are independent. Already you have considered this transformation. X equals to r cos theta. Y equals to r sin theta. R is greater than 0. Theta belongs to minus pi to plus pi. Already you know. Okay, so by definition, r square is x square plus y square. Is it okay? Any trouble? Now can you tell me what is the distribution of r square? You have two choices. Either you can get it from the definition here, or you can make a transformation from this distribution to r square. You can say z equals to r square. You know the density of r, and you can obtain the density of r square. Already from the previous method that you have learned from one variable transformation. So whatever may be the way, can you please tell me what is the distribution of x square plus y square? Already we have studied in our class. If xi, x1, x2, xk, so let me tell you once again, remind you that if xi's are IID normal 0, 1, sum of our xi square, I running from 1 to k, what does it follow? Check your note and tell me.
Sir, chi-square.
Chi-square distribution with k degrees of freedom, right? So what this will follow? Chi-square distribution with how many degrees of freedom?
2.
2. Okay. And also you know chi-square k is equivalent to gamma k by 2 half. This is alpha, this is lambda. Okay. So this is equivalent to gamma 1 half. Is it okay? This proof also we have done. At least this one we have done, chi-square. Chi-square and gamma equivalent. Okay. Now, if it is gamma 1, so gamma 1 half, and that is equivalent to what distribution? Gamma 1 half.
Exponential.
Exponential, correct. It is exponential half with lambda equals to half. Gamma 1 half is exponential half. Okay. Now, can you tell me that how can you get exponential half distribution from uniform 0, 1? See how we have done in our class. Let U1 follows uniform 0, 1.
So it's minus 1 by lambda log 1 minus
Yes, yes.
uniform 0, 1.
Uniform. So if U is following uniform 0, 1, then let us consider that minus lambda, lambda is half here, so minus 2 log of 1 minus U1 should be, but again notice this thing that U1 is distributionally same as 1 minus U1. Both of them will follow. This notation stands for they are distributionally same. Their CDF are same. That is what it means. That doesn't mean U1 equals to 1 minus U1. That is not the meaning. This means that same CDF. This means same CDF. Okay, this is a standard notation in probability. So we can write this quantity as U1. This is following exponential half. Okay, so this is the known result from our previous classes. So let us try to make the connection, and This thing you can make it from minus pi to plus pi, or you can also make it from 0 to pi, 2 pi. It has no problem. In any way you can take it, it has no problem. So if we let another random variable, let u2 is following uniform 0 1, then how can you make the transformation such that you will get a random variable which is following uniform 0 to 2 pi?
So just multiply it with 2 pi. Yeah, multiply
Yes.
uniform 0
So,
1 with 2 pi.
right. So 2 pi times u2 is following uniform 0 to 2 pi. This is also the known result from our previous class. So now let us see, can we assign this variable to r square and this variable to capital theta? And can we say that if I write where so u1, u2 are IID uniform 0 1, x according to this construction is square root of minus 2 log base e u1 multiplied with, that is, this is r cos theta, theta is 2 pi u2, and y equals to same thing r log base e u1 sine 2 pi u2. And then x and y IID normal. Can we do that? You generate random variable from uniform 0 1, uniform 0 1 independent, then consider this transformation. What you will get as x is following normal 0 1, what you will get as y is also following normal 0 1, and they will be independent. And that is the Box-Muller method. We need pair of independent random variable uniformly distributed, and from there we can get a pair of random variable which are independently normally distributed. Now, is this construction clear now? Why Box-Muller method that we have seen in the diagram works in this way? First, we have tried to identify what is the distribution of the radius. Already we have got, if you start from here and take the transformation of for distribution of r square, again eventually you will end up here. Okay, that derivation we have avoided. From definition we have started, and it is exponential half. Exponential half we can obtain easily from uniform 0 1. Uniform distribution for theta is easy to get. Now just you replace the variable in the equation. and you get the final result. Already this is known. Okay. Now let us try to see how you can obtain some distribution, or say for example a joint distribution, dependent distribution of x and y, where the marginals might be known to you. So let us try to see that. So this is the, let x and y are IID normal 0, 1. Find the distribution of, so I'm leaving this one as a homework. Z equals to rho times x plus square root of 1 minus rho square times y. Okay. And second, find the joint distribution of this x and z. Now, what you observe these two results, you will find something interesting. So, what is the transformation for xy to xz? You can write in this way that xz equals to 1 for z. This part is rho, this part is square root of 1 minus rho square 0 xy. Can you write it? This and this, it will give you x. This and this, it will give you z. Now, immediately this, from here you will get the Jacobian matrix and all those stuff. You know what to do. You will be able to see that how you can generate dependent normal distribution from independent normal distribution, where rho lies between -1 to +1. This is the representing the correlation. Okay, so this is one homework that I am leaving. Sorry. Okay, so another homework that is also interesting, people. Usually you may get this kind of question in your exam. Yeah, this is a very common question for your exam, any. So fxy equals to √3 divided by 4 pi e to the power minus x square minus xy, sorry, x into y plus y square whole divided by 2. Find the marginal PDF of, find the marginal PDF of x and y, and find the conditional PDF of say y given x. Also, you can try for x given y. So this is a very common question for exam, or this type of question are very common in exam. Don't forget to solve it. Okay, so now I'm trying to show you another result, which is little bit different, and the method of transformation is also some not the usual. Yes, so let us do that. The rest of the thing are as trivial as we have done. 27. So let example how many we have done. Let x and y are following IID normal 0, 1. Okay. Then find the PDF of u equals to x upon y. Okay. Now, for this kind of problem, when you are asked to find the density function of random variable or density function of a random variable, which is a function of more than one random variable, then usually what we do that we make the transformation from space of same dimension to the same dimension and then integrate out with the unnecessary variable. So consider from xy to uv in this kind of transformation where u equals to x upon y and v equals to say just y. Okay. This is the way. Then we will find the joint density of u and v, and then we will integrate out with respect to y, and we will get the density of u. Okay. So this is the strategy, and this is a common technique for many situations. Maybe we will see more in our future classes. Okay, so it is trivial. Now, can you please tell me how we can write x and y in terms of u and v? X equals to uv and y equals to v itself. Okay. So del xy del uv, the Jacobian, what it should be? Tell me.
So
V
v0.
V0. Okay, you are going in the, oh, whatever may be, it will be the same. Either you put 0 here, u here, or u here, 0 here. So it doesn't matter. 1.
So
Okay. Yes.
V is determinant.
No, it doesn't matter. Then this implies determinant of J is V, and the absolute value of determinant of J is mod of V. Okay. Now routine job. Joint density of xy is fxy e to the power minus half x square plus y square divided by root 2 pi square. Okay. That's it. Then the joint density of uv, say GUV. Here I need to plug in e to the power minus half. Okay, x square. X square means u square v square plus y square. Y square means v square. Okay, whole divided by 2 pi. Jacobian mod of v. Okay, don't forget to write the mod. Is it all right? And from here you can notice that u belongs to R, v also belongs to R. So this is the joint density of u and v. Now if you want to get the marginal of u, so GUU is GUV integrate over v dv. That is what you need to do. But I hope this is a trivial job for you. So this is what you can also write in this way, e to the power minus half v square, if you take out 1 plus u square mod v whole divided by 2 pi. Okay, so this is integration from minus infinity to plus infinity, e to the power minus half v square 1 plus u square mod v whole divided by 2 pi. But notice here one thing, that this is an even function of v. So what you can do, you integrate 0 to infinity 2 times of this integrand e to the power minus half v square 1 plus u square v dv whole divided by pi. Is it okay? Now you tell me what will be the final answer. Do this integration with respect to v and tell me the final answer. So you can take the transformation like half v square equals to z, and v dv will be your dz.
So it will be 1 upon pi into 1 by u square plus 1.
1 by u square, right?
Yes, sir.
So can you identify the distribution?
So Cauchy.
Cauchy, yes. So if you see where we have done Cauchy distribution, we have written this thing that u equals to x upon y is following Cauchy 0, 1. Okay, now I will give you few remarks and conclude today's class. So here few remarks related to Cauchy, that when x and y are IID normal 0 1, A is x by y is following Cauchy 0 1, B again the same way you can prove x by mod y is also following Cauchy 0 1. Okay. Even though if x and y, so this is 1, 2, are IID normal 0 sigma square, then also x by y is following Cauchy 0 1, B x by mod y is also following Cauchy 0 1. Okay. Now the third property that we can say here like this, x, so x by mod y, which is nothing but x by square root of y square, which is nothing but sorry, x by square root of y square divided by 1, and from definition what does it follow? You can start with either 0 1 or 0 sigma square, no problem, where x and y are IID normal. Okay, so let us consider x, y are IID normal 0 1 for the simplicity. Can you tell me the name of this distribution?
Sir, T distribution.
It is T distribution with degrees of freedom 1. Okay, and moment does not exist for Cauchy distribution. Don't forget that. Moment doesn't exist for Cauchy distribution, as a consequence T1 distribution. So if you see, maybe here also we can draw it. So if this is the normal distribution PDF, this is for normal 0 1, then then Cauchy distribution will have a less peak and thick tail. Okay. This is Cauchy 0. Okay, so if you let us see the PDF once again. I forgot whether I have demonstrated it or not. Let me just. Okay. Here, the T distribution. Yeah, you see this diagram. This dotted one is the normal 0 1, and this solid curves are for T distribution with different degrees of freedom. So T1 has less peak, T2 has little higher peak, T3 has little bit more higher peak, and so on and so forth. And as the degrees of freedom n is going to infinity, then T distribution eventually converts to the normal distribution. We can prove it mathematically, but for that we need little bit more stronger result. That result completely we will not be able to cover in this course, but we can state this thing that when if you have a Tn distribution, that means T distribution with n degrees of freedom, and when n goes to infinity, then the distribution will be same, or PDF will be same as the normal distribution, or the CDF will be same as the normal distribution. But for the purpose, if you really want to see it numerically, so let us make the statement that Tn distribution will converge to normal 0, 1 when n goes to infinity. So, but even if your n is near around 1000, then also you may find discrepancy in the probability value in the third or fourth decimal places. That I am telling you. But well, people often use even normal distribution after 100. That's acceptable. So that's it for today. Tomorrow we will try to study this convergence notion. That means the law of large numbers. That is the thing we will try to cover tomorrow. So before we leave, any quick question? I think we are running out of the time. If you have any query, you can ask. Otherwise, you go for your next class. And I think the Moodle has opened the class test 1 and class test 2 for your review. And I will try to get it done for class test 3 also quickly.